Hi everyone, welcome back once again. Let's continue the design of our continuous one-way solid slab as per the Eurocodes. Now this is the part 2 in which we'll be assigning the area of reinforcement as well as we'll be checking the deflection. Okay, so this is our example, and the only tiny change that I have modified here in this example is that I'm taking the permanent load as 6 kN per meter square instead of 5 kN per meter square, and I'm including the self-weight of the concrete. Okay, don't worry about the self-weight of the concrete, because here I'll be assuming the overall depth of my slab, and if you are not sure about how to calculate the self-weight of any structure member, then that's okay, we can do it. I'll show you how to do it, but in this example it's given. And well, without any further ado, let's get started. So to give you a very quick recap about what we had in the part 1, you see that we had this example and we were asked to design this first floor. We were given the loading, okay, the permanent as well as the imposed load, and that by designing one bay, then other bays, bay 2 and 3, follow suit. We took 1 meter strip and we said it's a continuous, so obviously that's a continuous solid one-way slab, and that just by multiplying the 1 meter strip by the loading, you get it in kilonewton per meter. Alright, then we moved to this part. In order to define or to work out your bending moment of the shear force, you're gonna need to refer to a method in order to determine the moments and the shear forces. Now, in order to do so, and knowing that our system here is indeterminate, that means it takes time in order to find or to work out the bending moment. But here is this method of coefficients. That means you don't have to worry about the calculation. You can simply find the bending moment and the shear force using these coefficients given in this table, and the only thing is that you have to meet certain conditions. We discussed about these conditions, and we said we saw also that all of these conditions are met, okay, in our continuous one-way solid slab. That means this one gives you a green light to go ahead and, well, take the coefficients and work them out. And then we talked a little bit about moment redistribution and how they are useful for us for our design. We also talked about the loading, types of loading, whether it's taken like maximum, minimum. That's whether you take it adjacent or alternate. So, well, for those who are not, for those who did not watch the part 1, I highly recommend going back there and watch it again before we start this part. Alright, so what we need to do here is that we need to work out the moments for the supports and for the spans as well. Now I'm putting this reference, I'm putting the codes I'm referring to, okay, so it's not just the Eurocode 2 we'll be referring to, Eurocode 1, Eurocode 0, we also have the BS, and we also definitely referring to the UK National Annex. Right, so this is our example, and what we need now to do is to determine the design ultimate load, and that's simply by using this formula. Now I'm using this equation 6.1. remember in the code you have 6.1 A and B along with the 6.1. So 6.1 point says that you need to use a partial factor of safety of 1.35 and 1.5, and then in order to find the ultimate load in kilonewton, I'm multiplying this, okay, by 2.5. 2.5 is the span, but we don't have one span here, we have 3 spans, but I'm being conservative and I'm taking the maximum span, which is 2.5. I need the F to be in kilonewton, not in kilonewton per meter. This is because when I substitute it here again in this moment equation, the unit of moment is kilonewton meter, so this one has to be in kilonewton, and then we have the span, which is in meter. Alright, so I'm assuming my overall depth, okay, my slab depth to be 170 millimeter. This is based on my experience. Now this is a small span. I can even go for a lower depth, but for the sake of this giving this example, I'm taking the overall depth h to be 170 millimeter. Now again, this is one method, okay, to assume the overall depth. There is another method which is by referring to the table that gives the effective span over the effective depth ratio, so that you satisfy the deflection requirements. Okay, you set your depth that it satisfies the deflection requirements, and this is the first step that we might start with in order like to give an overall depth of your member, structure member. Right, so what we have to do now, remember the self weight was already included in the example, but the way the simple way in order to find the self weight of the concrete, your structure member, it is to multiply the overall depth by the density of concrete times 1, the 1 meter strip, and gives you 4.25 kilonewton per meter. Don't include it because this one is already included in the permanent load. Alright, so my F, if you work it out here, it turns out to be 28 kilonewton. And as I said, we're taking the effective span to be only 2.5 meter, okay, as a uniform for all of the spans. And then simply, I've got the support moments, I've got the span moments. What you need to do is just take the F here and L, put it in this equation, and get the bending moment. Simple as that. Alright, now I have the support moments and I have the span moments. Now let's go to the member sizing. It is an essential part of the design. I assumed my overall depth to be 170 millimeter, but the very important term here and essential is the effective depth. I don't need the overall depth more than the effective depth. It is really an important term, and without it you cannot assign the area of reinforcement, you cannot check your deflection, so on and so forth. There are many things you will not be able to do without the effective, or without determining the effective depth of your slab. Right, in order to determine your member sizing, well, first of all the B is fixed, just 1 meter strip. Then in order to determine the D, okay, you need first of all to work out to understand the member durability and fire resistance, all both integrate into the into defining the overall depth of a member. And then member serviceability limit state, we talk about this later on. But first of all, let's talk about the nominal cover, which is here, and the durability. Okay, if you want really to understand the nominal cover, basically it's the distance between the surface of the reinforcement closest to the nearest concrete surface. Now I've got this building. Well, anyone would view this building as seen here on the right hand side, but any structural engineer will understand that it's like made up of these structural members. You have the slabs, you have columns, you have beams and footings as well. Now if you look at the members which are or pointing outwards, they are exposed to probably or maybe harsh conditions. That depends, okay, on the environment surrounding them. So for instance, this beam, okay, and this column here is exposed to well, extreme weathers, right? I mean, if you compare to the interior beams or the interior slabs. So members that which are interior would have a thinner, okay, cover compared to the exterior members, such as the plinth beam here. The plinth beam here should be thick, right, in order to resist all this kind of exposures, and that I don't want anything to touch my reinforcement. Okay, you don't want moisture to get inside it and deteriorate it. Okay, this is the last thing that you want to see in your design, because it will definitely reduce the lifespan of your structure member. You have the same thing for the slabs and for the columns. You see this column here, okay, I will not give it as deep cover compared to the column here extending from the footing up to the plinth beam. Okay, this is underneath the soil. so you have to protect it against what's in the soil. And for the footing, it has almost the thickest, okay, almost always the thickest cover to reinforcement, because the soil might have chemical attacks, okay, so it's underneath the soil, you don't know what's there, so you have to protect your reinforcement. So as an overall, our slab is just an interior member, and you don't have to worry about all of that. If you refer to this code, BS 8500 part 1, table A1, okay, this describes type of the condition that you are referring to, and I'm gonna have this dry or permanently wet, okay, for my slab. That's a big table, you can refer to it, you see all of the conditions there, pick up the one that suits you the best. For my XC1 is the best, describes my structure here, and that if you go back to table A3, you will see that for this exposure class, the nominal cover must be 15 plus DC, okay, and the minimum designated concrete class is C2025. That means I'm providing a nominal cover of 15 plus DC. This is the deviation, okay, delta deviation, and it ranges from 5 millimeter up to 15 millimeter. This is for formwork casting, okay. So I'm taking the deviation here, and it's under no QA, okay. I'm assuming this is under no quality assurance, so I'm taking the delta C deviation as 10, so I'm giving a nominal cover of 25, okay. That means whether in the support, whether in spans or supports, I'm giving a nominal cover of 25 millimeter. Right, remember also we have the concrete class, so the minimum is 20, but I'm taking 30, 37, and that's okay. Okay, and let's also assign the grade of steel. Let's beat the most common type, 500. So here I have the FCK as 30 Newton per millimeter square, and FYK as 500 Newton per millimeter square. Right, we are done with that. Okay, nominal cover, and now we can easily assign the effective depth. So 25 is the nominal cover, and basically you need to assume the diameter, rebar diameter, because I don't know what's the diameter of my rebar. That's my task. That's what I'm trying to design now. And then I'm assuming the diameter to be 12, okay? Because remember, the D extends from the extreme top up to the center of the rebar. So it's basically 170 minus 25, the nominal cover, plus that half of the diameter of my rebar, my assumed rebar. And then I get the D as 139, but I'm taking it as 140, and that's okay. Right. Another important term is the fire resistance, okay? It's measured by using this axis distance, half of the diameter up to the extreme bottom. And referring to this code, table 5.8, you will see that in my question, actually, they did not ask you to specify, or they did not specify the duration of fire resistance, but I'm assuming it will resist fire for 1 hour. That's 60 minutes. And then you see the requirements versus what I actually have. And then here in the requirements, the overall depth must be 80 millimeter, and the axis distance must be 20 millimeter. This is to meet the 1 hour fire resistance requirement. But actually what I have is that the overall depth is way higher than the required one, and the axis distance A here is just 25 plus half of the diameter, which is 6. It's here, and then I get it as 31. Again, this is higher than the A required, and that my slab will resist fire for 1 hour, and that's okay. Great. Now I can very easily and comfortably assign my area of reinforcement. I've got the bending moments, and probably the first thing that I might begin with is that you need to tell whether your structure is going to be singly reinforced or doubly reinforced, and this is such an important term. This is because if you get your structure, if you check the K here, okay, the K here, if you check it against the K prime and you find it more than the K prime, that means your structure is over reinforced, and that it's going to have a brittle failure. Again, that's something you always want to avoid. You don't want to have a brittle failure. you always want to have a ductile failure, and that's a behavior of a section that is under reinforced. So what I need to do here is basically determine the value of k, check it against the k prime. It must be less than the k prime, otherwise my section must be doubly reinforced. So the k prime here simply is given with this formula, and this delta here is the redistribution ratio. Okay, for my example, remember I'm using this table coefficients, and my redistribution, okay, is 20%. So my delta here is going to be 0.8. It's just 1 minus 0.8. Sorry, 0.2. It gives you 0.8. Okay, if that is if the 20% is my redistribution. Okay, so the k prime, if you work it out here, it turns out to be 0.153. all right, that means let's find the k here and compare it with this value. Okay, so my k, and I'm taking this largest moment, bending moment, okay, here, and then it turns out to be 0.01, which is way less than the 0.153. That means my section does not need any compression reinforcement. Okay, it is under reinforced. The failure should be a ductile failure. Okay, don't worry about this in the slabs, but in the beams you probably always need the compression reinforcement. All right, moving on. Now let's find the area of reinforcement. I'm taking the spans as well as the supports because they all have the same bending moment. 6 kilonewton meter. And then this is the area. This is the formula for finding the area of reinforcement. All of these are derived from the simplified stress block given in the Eurocode 2. And you see here, okay, we have the Z level arm. This is the formula for the Z, but you have to compare it with this limit, 0.95D. Anything you get here larger than this one, then you cancel it, you take the value of this one, the limit. So in this case, okay, I've got everything, the K here, and it turns out to be this figure. If you compare it to this one, 0.5D, which is 140 here, it is 161.5, and this figure, okay, the actual one is more than this one, so you don't take it, you limit it only to 0.95D. okay, and there you have it, the area of reinforcement required for the supports and for the spans. Simple as that. Now refer to this table, go back to this table. It gives you the bar size against spacing of the bars. Now 85.4, it's not given here. You can work it out, but it's not given here in this table. So instead take it as 94. Okay, this is the minimum. Okay, that means you have to provide 6 millimeter diameter bars against or in a spacing of 300 millimeters center to center. All right, again what's left is this one, the interior span moment, and we do exactly the same thing here. The moment is less, that means you get less area of reinforcement required, but again the provided one is going to be the minimum one, which is this one, H6 by 300 millimeter spacing center to center. Let's give us a summary. This is our continuous one-way solid slab, and that we have provided the bottom and the top rebars, which is H6 300 millimeter. Again, this is the spacing, okay, center to center, okay, and this is the diameter of my rebar. But one important thing is that this is not the final, okay, layout of the reinforcement. We will be changing this because we have to verify it against the minimum area of rebar required. Don't think this is the final one, okay? You have to go through detailing. We'll talk more about that in the next part. Right, so here's our section, and well, again, one very important thing that you have to go through is the deflection check. Okay, and let me try to illustrate all of that here in this example. Now I've got the simplest supported beam, I'm loading this, and then after a while you see this curvature developed here, and that I developed a slope. Now this beam will not collapse, okay, because I designed it against the ultimate limit state. It might be okay here, right? But take the same example and put false ceiling underneath your beam, just like anywhere in any building, okay, actual building. You see, after a while, okay, when the beam is deflected, the false ceiling is impaired. You see, it does not look good, and that thing we have to avoid. This is what's called the one of the checks, okay, for the serviceability limit state, deflection check, and we want to avoid this kind of deflection. This is done by simply increasing the depth of your beam. The thinner the beam, the more it deflects. So basically the code provides you with the two methods. It's either you calculate the deflection in millimeter, which is a lengthy, difficult process and not very common, okay, and the different and the more easy method, which is also very common, is to limit your span to effective depth ratio. Now this is the method I'm going to use, obviously. This method is very lengthy, and you find it again, you find your deflection in millimeter and then compare it with the L over 250 or L over 500, okay. But here in this method you don't have to do all of that. You don't have to find the deflection in millimeter. You need to limit your effective span of effective depth ratio up to this allowable L over D. So how we do it? Actually, I explained this in the in the simply supported beam design, one of my videos, but I'm explaining this again, and that's okay. Right, here is this method, the one that we are adopting in this example. Right, you have your L over D, the allowable one. The actual one I can easily calculate it, don't worry about this. Our focus is on this one, allowable L over D. It's either use this formula, the first one or the second one. That depends on the row and the row reference. The row reference here is going to be fixed because it depends on the grade of concrete, your concrete being used. And the row here is the percentage of reinforcement required in your section. Okay, the area of reinforcement required in your section divided by BD. Okay, that depends. This one would tell you whether you to use this one or to use the second equation. Okay, now you see inside any of these equations you have the K. It depends if you refer to this table from the National Annex, table 5. Okay, that depends, the K, the value of K. If it's simply important, then it's just 1. If it's an each span of continuous beam or slab, 1.3, interior spans 1.5, etc. So what do you have to do here is that, well, you have the K here, okay, you have the FCK, everything you need, you have it here. But then comes these modifications, F1, F2, F3. Well, starting with F1, it accounts for the flanged sections. Now for our example, we don't have any flanged sections, just a rectangular section, so the F1, you take it as 1. Okay, F2 accounts for the brittle partitions in association with long spans. Okay, if your span is more than 7, is 7 or more, then you have to consider this modification. Okay, it's by dividing 7 by your effective span of, suppose your beam, you have your beam at like 8 meters in span, then just 7 divided by 8, take that modification, put it here. Okay, my beam is just 2.5. I don't have to consider this modification, I just take it as 1. And the last one accounts for surface stress and tensile reinforcement, taken as the area of reinforcement provided over the required. Okay, this is a conservative way. There's another formula which I don't want to look at, or I don't want to go through right now because it's a lengthy, maybe nasty formula, but it's okay, we can go through that again. But I'm being conservative here. Maybe in the future, when we design a continuous beam, maybe I'll show it up to you and show you how to do it. But for the time being, I'm being conservative. A provided of A required. I should be less than 1.5, less than or equal 1.5. Right. So this is our example. Now, here's the value of K. That depends again. For inch span, it's just 1.3. For interior span, it's just 1.5. Now I have to take each one, but for the sake of saving time, I'm just taking this int span. Okay, I'm checking the deflection against this one. If this one passed, then most likely all of them would also pass. So let's just start with this one, and this is an int span. I've got the area required over the area provided. I have the k as well, and now let's see which one would I use, the first one or the second one. That depends on the row. First of all, the row reference is not going to change, just root 30. Okay, that depends on the grade of concrete that you are using. And then my row required over PD, it turns out to be very, very small, but you don't take it because the code also limits this value. It must be greater or equal to 0.0035. So instead of taking this small number, I'm taking the row just to be 0.0035. Okay, and to compare this one with this one. This one is obviously larger than this one. That means I'm going with the first formula. Okay, because here the row, okay, that I'm having is less than the row reference. My actual L over D, so it's 2.4 divided by effective depth 140, it gives you this number. This one I have to compare it with the one that I shall work it out very soon here in this formula. Right, let's look at the modifications. First of all, I've got everything you need here. Just plug and you see the modifications. The first one, as we said, just one rectangle section. Again, the second one, I have span less than 7, just take it as 1. And then here for the F3, this is the provided, and this is the required. It gives you 1.1. This is again less than 1.5. Alright, I've got everything that I need. Just plug and check. This is your allowed modified ratio, L over D. Okay, compare it with the actual one. You see that the deflection is satisfactory. Okay, the actual one is way less than the allowable one. That means deflection is okay. Now in this case, in this example, my overall depth is quite big compared to the span. Okay, and maybe if you get a smaller span, or if you get a larger span, say 5, 6 or 7, then you might need to refer this table to this table, and from here, because their slab is slightly stressed, you might assume your overall depth. Okay, for the continuous, suppose this one, the continuous, well, slab, you take the L over D equal to 26, but then you have to consider also the modifications. Okay, this would give you a good estimate of the effective depth, the D. Okay, instead of like going all the way back and revise the design, you might just jump straightforward into this table and determine your D. Alright, so we are done. Let's just give us a summary of the design. We're providing H6 300mm center to center for all the supports and spans, and this is what it looks theoretically. This is not the real look of the reinforcement. The layout of the reinforcement is way different, similar to the one you see here. Right, I'm not going to put this in any project. You never ever see it in this way, the layout of the reinforcement. You must see it in this formation. It might be more or less. Now the thing is, what kind of reinforcement? This top reinforcement, why would I provide top reinforcement here when I don't have any bending moment? Okay, and why do I have 2 layers of reinforcement, not just one? Okay, this is the first one and this is the second one, either for the top or for the bottom. And do I have to keep the H6 300mm? And why would I leave a gap here, an empty gap? Do I have to keep it like empty, or do I have to provide any kind of reinforcement? Also, to what extent do I have to extend my reinforcement? I know this is a negative bending moment. I have a negative bending moment here, but to what extent do I have to extend it? These are questions. We'll answer them in the next part. Okay, you will see the detailing of our slab and how to transfer your slab from this look to this look. This is what you need to give your contractor. Okay, otherwise this is not adequate. You cannot put it in this way. We're done with the part 2, and well till then, thank you very much for watching, and I see you very soon in the next part.